Good evening, or should I say good morning. As you know, this is pre-recorded. Welcome to part 2 of the binary populations lectures. Hopefully you're all okay. Hope you had a good first day, and I hope everything's going well. I think everything's okay at the moment. The fridge is rumbling a little bit. I apologize for that. I can't do much about it, but at least the good thing about recording in the evening is there's less lawnmower noise because it's dark out there, so there won't be any of that. So hopefully everything's okay. We've got here, I've got the slides up again. I've always wanted to do this, of course, just to say hello to everybody, and I hope everything's well. So let's go on with part 2. Let's have a quick recap of what we did in part 1. This is part 2, as you see. We've got an opening slide just to remind me in case anybody looks at this video again. What did we look at previously? So we had a long look at what population synthesis means, why it's useful, and we had certainly a good look at the big binary parameter space. And we discussed in detail how to sample that space effectively. There's no good answer to how you should sample things effectively. Really, you have to use your brain. But there are people who've done it before, and logarithmic grids, for example, choosing whether you want a Monte Carlo versus a fixed grid, and that kind of thing is very useful. You should certainly think about it before you go and do the hard work of throwing CPUs at this. We also looked at initial distributions. The initial mass function, if you've never heard of it before, is vital in this. There's also mass functions of secondary mass and things like that. And we'll look a little bit more of those in due course. And we also discussed fast synthetic stellar evolution models, because simply put, if you want to evolve 1 million stars, doing it with a detailed stellar evolution code is something I don't recommend you do, because if you're just starting your PhD now, you won't finish anywhere near half those models before you are at the end. And if you do, you'll discover a mistake and you'll have to do them all again anyway. So I would highly recommend learning a little bit about these fast synthetic stellar evolution codes. So what's coming up in this second lecture? Well, it's going to be sort of half, or maybe 2/3 of a bit of theory, a bit of showing you how theory compares to observations. That's the thing we need to compare to. Also discussing a little bit the selection effects, because those are very important when you compare to any survey. And then we'll go on with the next half. We'll talk about the power of population synthesis. So we'll look at the binary stars, and then I'll look at my binary C code. And the reason that I give that to you is because it's available for free. You can just download it. It's more than 20 years of work in there. And then we've got a lot of examples for you. So especially if you're into Python, you can do it with Python. There's other languages as well. You can do it in the shell. You can do it in Perl, whatever you want. But we've got a lot of new examples which are there in Python, which is stuff that we've been working on recently. And it enables you to use the code with other codes. As you saw today, there was a slide that was shown at the beginning. I think Andreas showed it, where you can see how you can then tie in binary C to all kinds of other things. So a lot of case studies that you can look at as well. These are things that if you want to really understand this, you can go away and read them and see what we've done. So let's look at observations. Now, why do I start a lecture on theory with a slide on observations? Well, however good our theories are, I think astrophysics is still observationally driven. We are still driven by whatever satellites we can put up, whatever telescopes can see for us. These are certainly absolutely vital for the things that we do. And I've put a set of surveys here. These are very much my selection. There are many, many others as well. I mean, there's a lot of ground-based surveys I haven't put here, but things like IMPRS and Gaia. I mean, you've got Gaia stuff coming up this week. You know exactly what that's all about. Other surveys that I've used in the past, things like SDSS, Apogee is a very good survey that I've used, and also Galar, which does chemical evolution of stars. These are huge things. And also astroseismic surveys, Corot, Kepler, things like that. And you'll hear more about that later on in the week. So surveys are certainly one of the ways to get statistics, okay? And that's fantastic for many things that you do. And a lot has come from Gaia already, and I think much will for 10 or 20 years based on I was still using Hipparcos 20 years after the data was out there. So it's still very important. However, a lot of stuff comes from sort of random pointings. What I mean by that is when people take a telescope and they go and look at an object that they find interesting for whatever reason. Now, particularly working in binary stars, because it's so difficult to find time on telescopes to do surveys of binary stars. I mean, they do exist, but it's very hard to do, and it's very hard to get the time. So it's often you're just looking at your favorite objects. And so the problem then, of course, you have is this thing called selection effects. Now, particularly if you are looking at an object that you think is interesting, what is the selection effects? You've chosen it. That's your selection effect. It's your mind that's selected it. However, if your surveys are things like Gaia or things like that, then it's a lot easier because it's just you know the size of the mirror, you know how deep it can see. And so when you look at surveys, really what you want is a volume limited sample. Okay, that's the simplest thing and possibly the easiest one to compare with. Because if you take, say, a volume limited sample of the solar neighborhood, you'll see this quite often, that makes life very simple, right? Can't spell today, there we go. That makes life very simple. You just say we've got local stars, and as long as your neighborhood is not too big, you don't even have to care about the fact that the galaxy is a disk. You can just say, for example, until very recently, all white dwarf surveys were essentially only complete out to a volume of about 20 parsecs, which is thinner than the disk. So very easy. But of course, if your volume gets larger, you then maybe do have to think about the galactic structure that you're looking at. So that actually can get a little bit complicated. So you've got to be careful in that regard. Now, magnitude limited surveys are more typical. Magnitude or luminosity, of course. But you can then say, well, okay, so as you go out in distance, the luminosity of stars that you can see, it changes, and this is typical of what's sort of a Malmquist type bias. So you can actually you can compensate for this with a completeness function. It's not too difficult to do. Now, what would be called a complete survey is rare, but it is possible. For example, if you look at the barium type stars, the survey of those is essentially complete because all of the giants we see in the sky, it's very easy to spot whether they're barium rich by looking at their spectrum, even a low resolution spectrum. And all of those we now have good, pretty good spectroscopy on. So in some cases a survey can be complete. Now, a random choice, I say random choice, this is your favorite stars, that might be okay for a survey if you have sufficient number of stars to justify the risk of choosing these stars. However, I should say also I've written papers on objects which are peculiar, and they were found by random chance often. And a lot of these observations also go back to the 60s, 70s, 80s, 90s, before the digital age, really. And this may be all the data you can get on these objects. I did a paper on merging red giants and looking at FK Comey type stars, and trust me, most of those are observed by luck. People go out, they make surveys, they see stars, they happen to be rapidly rotating red giants. Nobody, as far as I know, has gone out of their way to really go out and look for these stars particularly. That's because it may not be possible. You may have to observe lots of red giants. Kepler's done some of these, which is great, but again, you're just relying on a bit of luck to find them. So that might be all you can get, and that's fine. So you then need to think about how are we factoring in, why are we looking at these stars, and what are the biases involved. So it's not always simple, but you need to know that to compare your modeled populations to observations. Now, when you do have your observations and your models, and you've taken into account the selection effects, you say, well, which is best? Which model fits the observations best? And here I have observations are these blue points here. And of course, these are completely made up observations. And which of my two models, the purple line or the red line, is best? Well, clearly the purple line, right? So that's easy. And this is what we would call by-eye fitting. And you'd be surprised how often this gets you quite a long way. But it's not the way you would do things in the modern world, of course. You would use statistics. However, you might then say, well, okay, I've got here two sets of models, the blue models and the red models. These are two different stellar tracks, sets of stellar tracks. And I've got the observed stars, which are the grayscale. Okay. And these are a set of massive stars, and these are just Hertzsprung-Russell diagrams, or spectroscopic Hertzsprung-Russell diagrams. And it's a log scale in the number of objects, density. So the density, the grey density is log of number of objects. And I ask you, which is the best fit? Now, even by eye, it's not obvious which is the best fit, because this one on the left here, you see the red giant branch here, fits much better than on the right. So you say, so the models on the left, the Geneva models, they're much better, because they fit better. But then if you look at the zero-age main sequence, actually the fit up here is better in the Bond models, which are on the right, compared to the zero-age main sequence. And you might think, well, that's okay then. And the Bond models don't have very many up here, whereas Geneva does, and there's no stars up there at all. But it's very hard to come up with a quantitative way to say which of these distributions is best. So you have to think about that. It's quite complicated to compare these two. And then you can say, well, what if I make my models rotate? And it gets even more complicated after that. So that's the orange and green that are now plotted on top. It goes on. You can construct more and more model sets and compare them to your observations. It's very difficult to say which is better. Now, a simple way of doing it is to use something like a chi-squared. Where your chi-squared distribution, you've probably done this in school. The chi-squared is a function of the number of observations. This is the degrees of freedom here, number of observations, the number of parameters, and so on. But it simply boils down to the sum of the squares of the observed value, which is your O here, minus your computed value divided by the square of the error on the observation. Note there's nothing in there about the error on the computed value, which we assume is perfect, of course. We know that's not true. We discussed that a bit previously. We have systematic errors and also maybe counting errors that we try to minimize if we can, but okay. We hope to pin down what those parameters are by reducing this. You want to minimize your chi-squared. This is a standard problem that you do in school statistics or undergraduate level statistics. Nothing particularly thrilling here, except that it forms the basis of actually some science that we did. And we used this back in 2014 to compare these models. These lines here are models, and these points here are observations. And these are different chemical abundances in stars, particular, I think these are AGB stars, carbon-enhanced metal poor stars, I think. If you've never heard of these, these are stars out in the halo of the galaxy, very low metallicity and high carbon abundance. So, now, what you do is you calculate the observation minus the model, the computed model, that's easy, and then you sum up the squares divided by the error bars. It's very easy indeed. And you say, well, okay, this star is clearly a bad fit. We've got two models here. One gives a chi-squared of 12 and one gives a chi-squared of 26. That's not a good fit. So we say, well, probably this model does not give us this kind of star. Okay, maybe that's okay. I mean, indeed, in some other cases, we got chi-squareds down to, say, 1.2, which is very, very small indeed. And that suggests that for this particular star, this model makes sense. It's a different carbon-enhanced metal poor star. But you can do this because we can compute these models, and we did this with binary C. It's very, very, I say very easy. It's not easy to do, but you can do it. Did it for whole populations of stars, and we came up with, these are the parameters for the stars. These are the binary masses. This is the mass of material that is neutron exposed. This is what happens on the AGB. You have nucleosynthesis, and so on. And you have different parameters in the model, and you say which is the best fit model to the observations. And that we had a best fit model at all was great, because I didn't expect to get any models that fitted perfectly or fitted very well. So that, you can do things that are quite good, even with a simple test like a chi-squared. You can do other things to improve your fit. If you've got a multi-parameter space, you can do things which essentially are based on the amoeba or the downhill simplex type method. Even when people do Markov chain Monte Carlo, they're essentially doing the same thing. It's just using a slightly better way to do it. But you can find this if you look in numerical recipes, which is a classic book that all of you who do computational physics should have a look at some point. It will explain to you how to do this. And if you don't know the book, first author is Press et al. very famous people in physics that are in charge of this. Hang on, should move my head if I can. Oh, there you go, so you can see who it is. What this does is you're trying to find the minimal location of a function. You start at a position up here and you take some random vectors and you move down here and you use the gradient of descent so that wherever you start you will head towards the minimum. And you see I've got 2 attempts to do it here. One got there quicker than the other because there's a little random element to it, which makes sense. That's a very basic idea. It's good that you understand the idea because then if you go on to Markov chain Monte Carlo methods, they are the same idea essentially, your minimization of a function. So there are other methods out there. Move myself back. Other methods for matching your observations to your computed models. There are things like genetic models. I don't know if that's something that people do still use these days, mainly in biology, I think, but they're still used. Markov chain Monte Carlo, also called MCMC. This is very common. It's similar to the amoeba, but it involves a much smarter way of guessing what those vectors are as you move down into the minimum. This was often used even 20 years ago in cosmology. It's now used much more often in computing. For example, how good the match is between single stars and stars that you see in the sky, that kind of thing. It's a whole branch of numerical analysis, of course, to determine how good these models are. And indeed, there are many different Markov chain Monte Carlo models. And not only am I not the right person to talk about that, I also don't have enough time to really talk about that. However, one thing we should talk about are Bayesian comparison methods. This is a different way of thinking. The question is just comparing the observations minus the computed model good enough? Now, Bayes would say no. And if you don't know about Bayes' methods, I really highly recommend you go and you get a good textbook, read some. The Wikipedia page is a good place to start. Even YouTube, there are lots of introductions to this. Now, the reason for this is that if you use Bayes' theorem to compute the probability of A given B, and it comes out to this, probability B given A times the probability of A divided by probability of B, very easy to show this, you have to include the prior knowledge that you have, which is something you don't do with a chi-squared, for example. Okay, so you have to include the prior knowledge, and it can also give you distributions once you've been through this analysis of all of the parameters that you try to fit, which is great because then you know how well your model fits. Instead of just saying it's the best fit, you say it's the best fit with this error bar, which is what you want from science, right? Science is about the numbers. It's not about just saying this is good, this is bad. It's about saying how good, how bad. And to give you a case study, we did some work. This is with Fabian Schneider, who you met today, I hope. Good luck with the Mesa stuff. I saw all the errors. That was great. I'm glad I'm not the only one. We have a case study here, which is just we're trying to match a star that was observed. And when they observed it, they thought it was 27 solar masses, plus or minus about half a solar mass. These are observations of a particular star. This one, it's a telephone number. And from the observations, you have log G, effective temperature, and log luminosity, which are the standard things that you get from spectroscopy. Spectroscopy, of course, will not usually tell, well, it can't tell you the mass. It will tell you other things about the atmosphere of the star, but those are not uniquely mapped to masses. So you then have to go away and say, well, okay, given these observational luminosity, temperature, and gravity, what do we think from our models is the best fit? And we did a Bayesian analysis of this, and we got this value here, which you can see is nicely consistent. We also get from that the age, because in the models, you know not just the mass, you know also the age of the star. So now we know more things about the properties of the star, having done an analysis like this. And this we did some years ago. This has been worked on since, and Fabian can tell you all about how this is doing now, but it's still, I think, a very powerful tool. Now, why do I say it's a very powerful tool? There are many Python packages for doing this. The MC package is very popular. There are others that are variants on this, but it's very easy to use. And there are many papers on AstroPH also describing all of these things. So you can see there's a very vibrant community. And that I think is a great thing, that you have a vibrant, open community where people put their code out there so that other people can use it, which is absolutely the way to go. We get error bars. We get constraints. We also get to bootstrap the simulations, which is what that means is that you run it, say 10 times, 20 times, something like that, and you can then get an error bar which is based on the resolution of your model, for example. And you can make that match the number of stars you observe if you're looking at a survey. And then you can say, what do you think the natural counting error bar should be? Very powerful way of doing things. This is from a paper that I've currently got with a journal, but I put it in here anyway. This is comparing a model of a disk around, it's a circumbinary disk around a star to an observed disk. And of course this disk has parameters, which we call alpha, f, t, fm, and fj. Don't worry about what they are. They're to do with the mass of the disk, its angular momentum, things like that. And we ask the question, well, how well do we pin these parameters down given these observations, which are pretty good now because they're from ALMA, they're made with ALMA. And indeed, we get distributions out like this for each parameter, where we say this is the best that we can say about what these parameters are. We also know you can fit a Gaussian to that if you want, or you can look for the 69% confidence intervals, and you can say, well, how wide are these Gaussian-like peaks, and how accurately do we know these parameters? And to do this, I just use binary C, which we'll talk about in a bit. And I used MC, which is very easy, and the giant triangle confusogram package, which is fantastic. Packages with names like that are there to be used. It's the best one I found so far, I have to say, for this kind of thing. But if I can do this, you can do this, because I did this in about a couple of hours from scratch, not knowing anything about how these things worked. So if it's that easy, you can do it. So let's have a quick recap while we're here before we go on to the next section. So we've discussed what a population of stars is. We know how to distribute stars, so we know the initial mass function and things like that. We know how to make population statistics, and we know a little bit about how to compare with observations. I mean, that's a whole thing, but it's still, we've touched the surface, so that's good. But we still haven't gone on to the next part, which is binary stars. We've talked a little bit about binary stars, but we haven't really said what they are or why we think they're important. Now, what are they? The most basic thing is here. Two stars bound by gravity. Okay. So a star is bound to itself by gravity, of course, but when the other star is also bound to it, you end up with a binary system. And the thing that stops the stars merging is that they have angular momentum, this orbital angular momentum. And that means that they travel in ellipses, as Newton showed a very long time ago, and Kepler as well, of course. Maybe Kepler showed that. Newton came up with the gravity as the reason why this is. A little bit on nomenclature here. The star that is most massive or most luminous is usually called the primary. Now, normally they are the same, not always. And the star that is the least massive or the least bright is called the secondary. You have to, when you're reading a paper, you have to make sure you know which is which, because it's not trivial often. If it's a theory paper, it's usually the mass, and if it's an observational paper, it's usually the brighter star is the primary. So just make sure you know. Now, Kepler has his famous laws. If you don't know them, there are 3 laws, Kepler's laws 1, 2, and 3. One of them says that the period squared is proportional to the separation cubed. And that is absolutely vital. That's true for the Earth going around the Sun. It's true for any 2 objects traveling around each other under the force of gravity. Okay, so that's very simple. And then Newton said, well, gravity is the thing that keeps the stars from flying away. It seems obvious to us now, but of course when these people came up with these ideas, it was absolutely vital and new, and no one had seen this before. So we use Kepler's law and we use Newton's law to do most of the orbital evolution of binaries, except for very close binaries like black hole pairs or white dwarf pairs that are very compact. Other than that, we don't need really to go into any gravitational radiation or gravitational GR type effects. Everything we can do pretty well with Newtonian physics. Now, what is the fraction of stars that are in binaries? Well, this turns out this is not a constant. You might think, well, we'll look up in the sky, see a load of binaries, just say that's diffraction. But actually, it depends on the spectral type of the stars. And so you see in the O and B type stars up here, most stars are in binaries. Diffraction is maybe 100%. That doesn't mean they're all interacting. Some of them are quite wide, but still, it's important to know that most of them are in binaries, or indeed triples or quadruples. It does go up. And in the stars that are the spectral types that are nearer to the sun, which is a K type, then you're looking at maybe 40%. Okay, so it's many fewer. And there are people who think that the reason you have these two branches is because star formation works differently in these two scenarios. And of course, these depend really on mass. So the spectral type you can map to mass on the zero-age main sequence, and the low mass stars have this sort of around 40% in binaries, and up here you have more than about 80% of the massive stars are in binaries. And then you can roughly draw a line between the two. Now, if you want to read up about this, I would highly recommend you go read the Mo and De Stefano paper, which is a 60-page paper on how to construct these kind of statistics. It's long, but it's really got everything you'll ever need on this. It's really, really good. And they've done some follow-up work since, which is fantastic. If you're worried about triple stars, don't worry too much. Make a few notes here for you. So in triples, they tend to be what are called hierarchical. And that means a triple is actually a binary and another star going around each other. So it's like a binary-binary. And the reason for this is that if the system is not hierarchical, they tend to have chaotic orbits and fly apart. Same for quadruples. Quadruples tend to be binary-binaries, going around like that, and so on as you go up. So the binary is really worth studying on its own, even if you're interested in triple stars or quadruples. You still need to study binaries and understand them. Now the primary mass, we've already looked at the distributions of these things. The primary mass in binaries roughly follows the IMF. It's not quite, but it's close enough, I think, for most work. Now we discussed the Salpeter IMF and we looked at the other IMFs a little bit as well. There are different IMFs out there. I mean, the curves look very similar here, but you'll notice they're quite different at this low mass end. So you've got to get the normalization right, otherwise that can all go wrong. There's a module out there on GitHub called the GalMF module, which is a Python module. So if you ever want to model IMFs, I would recommend looking at that. The reason I quickly mention that is because there's been quite a lot of work the last few years about whether the initial mass function is actually universal or it depends on scenario. So for example, if a star is born in a very low metallicity environment, is this distribution different? That's work I think that is still out there, and there is some evidence that it possibly is. But you can go and read that. Now the second thing we need to consider is the distribution of the secondary masses in binaries. Now we usually write M2 as this Q, which is the mass ratio. We write Q times the primary mass. Okay, now by definition, Q must be in the range 0 to 1, right? Because the secondary mass is defined to be less than the primary mass. That's how we define it in this. So the mass ratio is between 0 and 1, and indeed it's not quite 0 at the low mass end because there's a lower mass limit for stars, which is what 0.07 solar masses. And indeed it turns out that I got this data from the Duchenne and Krauss review from 2013, but it turns out this function actually depends on the primary mass. So it's not quite a trivial function after all. And indeed, what we probably should write up here is 5m1 and m2. So that makes it a bit easier. But the slope is, of the distribution is depends on the mass. Typically what you will see in papers, we use a color that's not on here, is this line here, which is straight across, which is a flat Q equals 1, flat Q distribution we call it essentially. So you get 1 between 0 and 1 because you have to normalize it. And what that means is that any secondary mass up to the primary mass is equally likely. And you see that's not a terrible approximation for these curves in most of them. I mean, for massive stars, it looks kind of okay. It's maybe not so good at 3 solar masses. I don't know. You can also look at the Mo and DeStefano paper from 2017. It's a bit newer, has a bit newer data, and will give you slightly updated numbers on this. And that, again, has all of this data in it. So we look at the mass ratio. That's the second thing we need to consider. And then the final one, you use Kepler's law. Remember, this is Kepler. Here, we can convert from the orbital period to the separation. So if we know M1 and M2, then we only need a distribution of either the separation or period. Doesn't matter which you choose. You can convert between the two. Now, period is easier to measure because when you look at observations of binaries, periods are relatively straightforward to get from spectroscopy. So we usually look at period distributions. And here, for example, we look at a set of O dwarfs and a set of GK dwarfs. The O dwarfs are from Sana et al. In 2012, it's 10 years ago now. It's amazing to think that. They peak towards the short period. Now, these are massive stars, right? These are 10 solar mass, 20 solar mass. These are really massive stars. And they have very short periods. And what that means is that there are a lot of massive stars interacting. The GK dwarfs are around 1 solar mass. They're in the Raghavan's paper from 2010. You see they have a very different period distribution. Indeed, they peak out to around 10 to the 5 days, which is very, very long. Remember, a year is 365 days, so that's what 300 years roughly is the period. So that's crazy. That's extremely long binaries. They're, you'll look at them on the sky in your PhD and they'll not move, so it's very hard to spot. So what that means is low mass stars are less likely to interact. So if all you care about for interactions are stars down here, for example, maybe less than 1,000 days, that's only a few % of low mass stars. But if you care about the interacting systems, let's see if we can find a nice blue, in massive stars, that's all of these. And so that's most of them. So it turns out that in the massive stars, most of them will interact at some point in their life. Now, we've neglected the eccentricity up to now. And remember, the eccentricity, if you have a circular system or you have an eccentric system, so this one has very high eccentricity and this one has E is the eccentricity usually, and if it's circular, E is 0. If it's eccentric, E is greater than 0. Now, we've neglected this up to now, and the reason for that is that in binaries, you have things like tides, which are important, which we'll mention a little bit later. And tides tend to make the eccentricity go to 0 when the binary is quite close. And so systems that start eccentric don't tend to be eccentric, and certainly when they're overflowing with Roche lobes, which we'll discuss in a minute, they will have eccentricities close to 0. However, if you look at stars when they are born, for example, if you observe them in clusters, such as Maibon and Matthew's paper from 2005, they've written some follow-up papers as well, which I highly recommend. You get a distribution looks something like this, which peaks at around E is 0.4. So it turns out that on the 0-age main sequence, the systems are born with a lot of eccentricity. A typical distribution used in models is this called the thermal distribution. It's a theoretical distribution based on, I think it's equipartition of energy or something like that. It's a long time since I've studied that. It's also used sometimes, particularly in globular clusters. Sometimes it appears like that, but I don't think it has an observational justification, really. It's very difficult to say. So if you're looking at interacting binaries, it's safe-ish to assume that the eccentricity is always 0, because the tides will force it to 0 every time. So that's not such a bad approximation. There are worse ones you probably make in the modeling. So then to calculate the statistics, remember I said before that we have to sum up over all of the stars. Well, that's, if you want to put them all in, that's these 4 sums here. And you probably want to you then have to loop over the time as well. And you have to do it for binary systems, which are this line above, and single stars, which is this line below, because that only depends on the mass. The star formation rate here, you've got the initial distributions here. This is your 1 or 0 function from the stellar evolution when you're counting numbers of, say, red giants. It's 1 when it's a red giant, 0 when it's not. And this is your time step. And you see that this sum is enormous. It's 5-dimensional. And each of those you need to resolve with maybe 100 points, maybe 1,000 if you're doing time distributions. It's very difficult to do. And then you've also got this here, which is the binary fraction, which we discussed previously. So it's a very complicated sum to do. You can do it. It's not impossible. But if you do it with high resolution in each sum, you've got 100 times 100 times 100 times 100 times 100 times. That's a lot of stellar models that you need to calculate. So that turns out to be difficult. So what we normally do is set the eccentricity to 0. That gets rid of this sum here. We set S to 1. So it gets rid of these star formation rates. Remember we discussed previously, we look at ratios of stars, then numbers of stars, then we can set S to 1. We fix the metallicity, so we only have to calculate one set of these delta bars. And, it's still at least a quadruple sum, but it's a little more tractable than it would have been if it were 5 of them and we had to vary the stellar properties as a function of, and the star formation rate as a function of time. And this is why these fast synthetic codes are extremely useful, because you need them to compute all of these things. Now let's talk a little bit about the physics that's important in binaries. Now, really here we're talking about things that are fundamental in all physical systems. So we have first the mass of the stars. Why is the mass so important? Well, remember, stellar evolution depends on the mass of the system. And the mass determines how the nuclear burning works in the core of the star, and hence the lifetime, the luminosity, the temperature, the radius, all these things. So that's very important. The masses then feed back into Kepler's law, and they give you part of the orbital dynamics. The other thing is the energy that you have to look at. And the energy is, of course, just the sum of the kinetic plus the potential energy. So this is your kinetic energy here, and this is your potential energy here. And in a bound system, that's less than 0. So the gravity wins, and the stars don't fly off to infinity. You can use the virial theorem as well to show that these things stay bound. If you don't know the virial theorem, go and have a look at it. You will need to know it. It's very important. The other thing that's important, and this is the other thing you require in order to calculate the orbits, is the angular momentum of the system. That's its spin, essentially. Okay, so that's absolutely crucial, and it's defined exactly as you'd expect from first principles. It's just the cross product of the position with the velocity multiplied by the mass. Very easy, or the moment of momentum, as some people like to call it. Very easy. But you can simplify this in a plane. If you work in the orbital plane of the binary, you can write this down as a scalar, and that makes life much easier. So if all the stars stay in the orbital plane, it's just a scalar equation. It's not a vector equation anymore. And that makes life much simpler for you because you can do the mathematics much more simply. So it's not quite as complicated as this equation may suggest. And most binaries we see are just obviously if you have 2 stars, they're obviously in a plane. You could ask what happens when the stars have a misaligned spin axis with the plane. But if you look at the tidal theory says, well, if that's true and the stars are reasonably close, then the spin axis should align with the orbital axis very quickly, in which case you can just write down immediately what the spin angular momenta are as well. And so it becomes quite simple. Now, speaking of that theory, we'll have a quick look at tides. Now, I don't want to go into tides in too much detail because they're not the simplest thing to look at. But the tides are the dissipation of the orbit that happens because of deformation in the stars. So if you have 2 stars, say here and here, this star will be deformed in bulges pointing roughly towards the other star. And the reason for that is that gravity is not constant across the star. The gravity is strongest here and weakest here because it's further away. And so you have this gradient of the gravitational force or the gravitational acceleration gives you these bulges. We see that on Earth, right? We see the tides on Earth. That's exactly what they are. Partly caused by the moon, partly caused by the sun. But we see exactly that. Now what the tides do is they synchronize the rotation rates of the 2 objects. So in this case, binary stars, the 2 stars will want to be synchronized with the orbit. So what happens is that the rate of spin of the star will then be the same as the orbital spin rate. And you can see that here because you've got this term here in the derivative for the rate of change of the spin. And then where omega is the, I think omega is the orbital and little omega is the, well, that can't be right. No, must be the stellar and this must be the orbital spin rate. It makes it easier to think that way. And the lowest energy state then has these two spins being identical. And of course, every system tends towards its lowest energy state. You can do similar calculations for the eccentricity of the orbit. So eccentric orbits have higher energy. And so if you can dissipate that energy, and tides are a perfect way to do that, you can circularize the orbit. And so you end up with if you go through a simple, I say simple, you read Zahn's papers from the 70s, good luck. Hutt's paper from 1981 is much simpler, much easier to understand, but you need to go through Zahn first, and that's the problem. They're the classics. All you have to care about, though, in these expressions are what I've boxed here and here, which are these terms where the tidal synchronization timescales and circularization timescales are a factor of the radius of the star divided by the separation to a large number. Okay, so it's R over A to something large. And what that means is that when the star is very small, R over A, of course, is also very small. And so the tides do essentially nothing. When R over A becomes large, so 0.5, 0.6, then the tides kick in and essentially turn on very, very suddenly. So tides are either essentially off or on. And it's not really true, it's a smooth function, but it's not far off an on-off switch. And so close systems will have tides that work very effectively, and distant systems will not. And indeed, you can plot the eccentricity as a function of R over A. As I said, once you get up to around 0.4, 0.5, these are all circular. So these have eccentricities here. Remember, eccentricity 0 is circular. And then you have this envelope here, which says, well, okay, so the most eccentric systems must have R over A that is somewhere that's small. So it's a small number compared to 1. And what this really means is close binaries are circularized rapidly. Okay, so this is why we can often say the eccentricity is 0. Okay. So now let's have a look at what's very important in these systems, which is, we'll talk about the equipotentials around the stars. So we've got two stars. One is at this point on the left here, and one is on the right here. And I've used a code to plot equipotentials. These are equipotentials of equal energy surfaces, which you could compute by just computing the gravity from the two stars. And you have to take into account the rotation as well, of course. Now these stars do not have the same mass because the star on the left is clearly, it's got a higher mass because it's got more equipotentials that you can see around it, so that are further away. So it's relatively straightforward, I think, to look at these stars and say, well, okay, what happens to the material that's in these stars? Now, as the stars expand, they will get old as they expand, right? So, rule of thumb number 1: as stars get old, stars expand. You know that from the lectures you had. I should say yesterday. They were today, but yesterday. Stars get old, stars expand. They're like my waistline, of course. This happens. There's nothing you can do about it. So let's have the star expand, and we want to see what happens. Now, before we do that, there are 2 points here which are important. There's this one here and this one here, and well, there's another one here as well, which we might want to care about. These are called Lagrange points, and those are points where formally the acceleration is 0. Now the acceleration is 0, you can think of if you have two stars and you have gravity from one and gravity from another, then there has to be a point somewhere in the middle, roughly, where the gravity is 0. It's not actually that simple because you also have to take into account the Coriolis force, because we're looking at this in a frame where the stars are stationary. But in a real frame of reference, the stars are not stationary, they're orbiting. So you also have to take into account the Coriolis force. bad at this at night. There we go. So you need the Coriolis force plus the gravity, and then you can work out positions. And actually there are 5 of these points. Now the most important for binary physics is L1, which sits between the 2 stars. Because when the star on the left here gets bigger and bigger as it expands, it will then hit L1, and formally that material is not bound at either star. But in theory, the star could then continue expanding and hit L2, or maybe even L3, which is over here. L4 and L5 are less important. They're off. They're out of the plane, so we don't care about them too much. But they are useful if you're working on satellite orbits, for example, or asteroid orbits around the sun. They're still quite important. So what happens when the star becomes a red giant, for example? It becomes very large, and it fills subsequent equipotentials as it gets bigger until it hits the point where it's at now this L1 point. And at that point, material on the surface is no longer bound to the star on the left. It's just as bound to the star on the right. And so it can flow through there in what's called Roche-Lobe overflow. And this teardrop shape here is called the Roche-Lobe. And we usually model that by saying, well, when the radius exceeds some other radius called the Roche radius, then the star overflows. And the Roche radius is actually set by comparing the volumes of the Roche-Lobe to the volume of a star to make sure you've got the same amount of material in there, essentially. If you care about what the Roche-Lobe radius is, it's a function of the separation of the stars and the mass ratio. And I highly recommend Eggleton's 1.2 page paper from 1983. Just shows you don't need a long paper to make a point. And that's one of the best cited papers, I think, in astrophysics. So it's really fantastic. But then what happens is the material that flows over to the right here flows down, and it can spiral in and it can hit the other star. And then you have to say, well, is the material accreted? Is it not? That changes completely the evolution of that star. So Roche-Lobe overflow, you'll see that everywhere in binary papers, is absolutely vital. And it's still not a particularly well, I mean, we understand that mass gets transferred, but whether that mass is transferred in a way that the material is kept in the system or is lost, still, I think, is a big question. But the simplest model of this is what's called conservative mass transfer. And this is where you just conserve your basic quantities. So no material is lost from the system. So that means that m dot is 0, which means, of course, that m1 plus m2 is 0. You can also then conserve the angular momentum because there's no material being lost to carry it. And so you say j dot is 0. And you know what j is because you can compute that quite trivially from the orbit equations. And you combine those equations and you end up with this equation here. And you can then plot this very simply as a function of mass. You can then plot what the separation of the system will be. And indeed, first the system contracts. And then when Q is 1, this is the mass ratio, so when M1 equals M2, then the system expands. And this is typically what happens in conservative mass transfer. And the trick is if you want to look at binaries that survive this phase, you don't want them to merge during the contraction phase, because if the stars get too close, of course, they will impact each other. This is not good. You also don't want them to get too close because tidal interactions, things like the Darwin instability, if you don't know about that, that's where the tides are so strong that in order to keep the system, to keep the orbit going, there's not enough angular momentum in the orbit anymore, and the system will just merge. The time scale on which it happens is not so trivial, but we're pretty sure this happens in close binaries. So conservative mass transfer is a very simple model. You'll see this a lot. It's something I just wanted to make you aware of. And so you'll see it very often. But then sometimes you can have also mass transfer that is unstable. So you don't really go through this conservative phase because you don't get a chance to. Now this often happens when you fill the Roche-Lobe with a star on the left that is a red giant. And this has a convective envelope. And the thing about convective envelopes is that as you strip the mass, so mass goes down, the radius goes up. okay, because they are convective. You can show this very easily. It's in all the textbooks. Akim will give you, I'm sure he'll give you a bit of an idea how to solve this. Now the problem then is, if you strip mass and the radius goes up, the star just gets bigger. So this star will then become this big, and then this big, and it's still transferring mass onto the companion. And eventually they'll fill subsequent Roche lobes until the whole thing is filled. And this is what we call common envelope evolution. So the two stars then are inside a shared envelope between the two systems. And what happens at the end of this? Well, you've got a choice. The cores of the stars can spiral in and merge, and so that's what this is on the left here. You can have a merger, or a merge, if you want to call it that. Or maybe you could eject your common envelope, and you've still got a binary, and you get this sort of wispy material flung off, and that may be what you see in planetary nebulae, for example. Some planetary nebulae may be like that. Now, of course, a merged star is still single. So you've taken a binary and you've turned it into a single star. So if you are looking, for example, for black hole merger candidates, if they merge prior to that in a common envelope, that's no good. They are not your candidates. What you want is a system that's something like this, but much more massive, like this one on the right. But you want much more massive, so they're not white dwarfs, they become neutron stars or black holes. Now, why do we care about this in binary populations? Because we want to estimate numbers of, say, white dwarf close pairs that may then merge and explode, numbers of close black hole neutron star objects that may merge and give off gravitational waves, this kind of thing. And we typically model it by looking at two numbers. One is how bound is the red giant's envelope. And we need to know this because if the red giant is very, very bound, of course, it's very hard to eject anything. We also need to know what is the efficiency of the ejection. And this is this parameter here, alpha. Now, alpha is related to how much energy is in the orbit that is then available for unbinding the orbit. So if you take alpha multiplied by the original energy in the orbit just before Roche lobe overflow, that is how you define how much energy is going into the envelope to try to unbind it. And from observations, typically alpha in cataclysmic variables is around 0.2. But when I say around 0.2, some of them are 1, some of them are nearly 0. It's a bit of a mess. It's not great. And it's very, very hard to know exactly what the value of this is. Now, typically lambda is around 0.5. In stars, it does vary quite a lot. But in normal red giants, it's around 0.5. Let's say that for now. And what you can do is you can say, okay, if I take this much energy out of the orbit and I put it into blowing off the envelope, which is what this equation says, how can I compute my final to initial mass separations? How much does my orbit shrink? And indeed, what I do here is I've run a series of models. So this is before common envelope orbital distributions. This is at the moment they start Roche lobe overflow. And these are two curves here with different alpha parameters of how close the stars are. This is just the cores of the stars, of course, because the envelope itself is stripped. And you can see that if alpha is smaller, these stars tend to be a little bit closer together. So if you want close binaries, that's these ones down here. These would be your white dwarf, neutron star type binaries. If you want those, what you want is for alpha to be not too large, because if it's too large, the orbit doesn't change very much. You could also say alpha must be less than 1, otherwise you don't conserve energy. That may well be true. Certainly, there isn't more orbital energy than all of the orbital energy to extract, but maybe there are other solutions to this. You may get energy that's from nucleosynthesis, for example, or accretion energy onto a compact object. There are ways to make alpha larger should you wish to, but I think it's best to say that we don't know what alpha is. And one of the approximations that goes into most of our models is that alpha is just a constant. We don't know. Now, I've made a notebook that we'll see in a minute, which is the binary C Python notebook. Please have a go with that, and you can make your own distributions, and you can do this experiment yourself. It's not difficult to do. Now, what did we get in these closed systems once they've actually gone through this common envelope mess? What happens to them? Well, the donors are usually red giants, so they're hydrogen shell burning, red giant stars, or maybe AGB stars, or maybe red supergiant stars. But they're still hydrogen shell burning, and so what's underneath there is what's left if they don't merge. So there'll be helium white dwarfs, carbon oxygen white dwarfs, oxygen neon white dwarfs, depending on the mass, and maybe an SDB star or an SDO star. These are helium stars. And if you strip the star at just the right moment on the red giant branch, you can turn a star into one of these. Now, you're then left with a system which has a white dwarf, if it's low mass, and that white dwarf can accrete from the companion star that survives in this relatively close orbit. And that may give you novae, which are thermonuclear explosions of hydrogen on the surface, and it may also give you type 1a supernovae, which is where you ignite the entire carbon-oxygen white dwarf. If you can do that, it goes bang. So it's certainly something that's worth attempting to model. You can also say, well, what happens if you go through two common envelopes? Which you could then do, because you've got now, after the first one, you've got a carbon-oxygen white dwarf and a star. It's just a main sequence star. That will then evolve, become a red giant, and that'll become a red giant and strip itself as well, and you'll end up with a carbon-oxygen white dwarf binary. That may also merge to become a type 1a supernova. And we can predict the numbers of these. This is from the last paper I was on, trying to do this from Yoka class back in 2014. And you can do a reasonable job of making the observations, which are the points with the error bars on here. You can make them agree roughly with the models that we have. And here we have two of the single degenerate models. That's this one here. Well, they're called single degenerates because it's a white dwarf accreting, which is a degenerate star, accreting from a non-degenerate star. Double degenerates are where you have two white dwarfs, so that would be this blue curve out here in later times. So we can make the models agree reasonably well. I think there are still discrepancies and still things we don't understand about 1As. For example, if you go to observe them, you don't tend to see the companions, which you should, which is a problem. Now, if you go to more massive systems, what you end up with is a neutron star or a black hole, often, in this post-common envelope system, where it can go through a helium star phase and then it will explode, because, of course, they have a core collapse supernova. Now, if the system survives the core collapse, which is unknown, because what will happen is there's a kick that happens, and we'll discuss this in a minute, but if it survives the kick in the supernova, you can end up with a neutron star with a companion in there, which is normal main sequence star, and that will transfer material over to the neutron star or black hole, which will accrete and will be very, very bright in X-rays because it's accreting at very high power. So these are what are called X-ray binaries. And these then, if the companion goes on to evolve, and you are lucky enough to survive a second supernova, then you'll end up with a system which is potentially a neutron star black hole type binary. Now these are going to be very rare, but when they do happen, some of them will be close enough for gravitational radiation to spiral them in. We know this because they were observed a few years ago. Now, you could say to yourself, well, how close do they have to be? Well, Peters in 64 wrote a paper on this, where you can compute, I think this is for a 2 + 2 solar mass system, you can compute the timescale on which these stars will merge because of radiation of gravitational waves. That's very easy to do. It's then just a function of their separation because I fixed the masses. And if you come down here somewhere, you get to around 5 or 6 solar radii. I think it's 6 solar radii if you want to merge in the age of the universe. Okay, so the stars that come out after you've had the common envelopes, after you've had the supernova kicks, have to be within 6 solar radii. Now the chances of that are small, but you've got a lot of stars out there, right? 100 billion stars in the galaxy, maybe a few million are going to be very massive, so it's not crazy. And in the early universe, it's probably easier. So the systems have to survive any mass loss. That can be the supernova and winds, because winds, if you have a wind, it expands the system. They have to survive the supernova kick. So what you need are lots of systems and a bit of luck. And then you can reasonably do it. But it's not easy to do. However, we can predict the numbers of stars that we get with these kind of systems. And indeed, this is something my PhD student David Hendricks has been doing. He's been computing the merger rates, which are on these top plots here. He's been combining them with a metallicity distribution, because it turns out that's very important. Because the metallicity of the universe, of course, in the old universe is much lower than it is now. And low is important because then you have less wind loss, so it's one fewer thing to worry about. So keep your binaries close. And you can weight your star formation rate as a function of metallicity, and you can see where your stars are likely to be born as a function of time. And then if you go through these computations, you combine all these things, which is, of course, multiplying through these things. This is the convolution we were talking about before, the big computations. You can compute things like this. This is called the chirp mass. This is very important. This is what dominates the orbital evolution of gravitational radiating objects. It's just a combination of M1 and M2. You can compute the chirp mass, and the great thing is you can also observe the chirp. Well, you can calculate the chirp mass from the gravitational wave observations. So it's relatively straightforward to go from the chirp mass in the models to the chirp mass in the observations. And you can make predictions of these. So this is a look back time here. So this is the Big Bang over here, and this is now here. And this is just the distribution of the chirp masses that you expect from the models. And it's on a log scale. So the brighter colors here, the brighter yellow is much more likely. You can also predict the total mass. So this is the total mass of the system, M1 plus M2, also as a function of look-back time. And it's similar, it's a similar distribution that you'll see, but it's a slightly different number, and you can also get this out of the observations. And this, of course, is what's important, because some people think that there's a gap in this distribution. Some people think there isn't a gap in it. I think it's still an open question, to be honest. I think the statistics aren't great yet, but we shall see. But we can predict this from the models, and you can convolve these now to say, well, what should we observe now based on these systems that have evolved in the past and then traveled, gravitational waves travel through the universe. You can do all of these, fold in the selection effects, and then compare with the observations. So we can compute distributions of chirp mass and total mass, and well, maybe there's a dip here. I don't know, maybe, not sure. Not sure I believe that. We've had a lot of discussions about this, but you can make these computations, you can compare. There are people, for example, the Compass code group, they have a synthetic code that they use to do this, and they do it with full Bayesian, and it's kind of fun for them. There's a lot of important physics we haven't discussed today because time is limited, and it's all in the code if you want to try it out. Things like wind accretion, we talked about gravitational radiation. Helium stars we touched on very briefly, but not hugely, but most helium stars you probably make in binaries, especially at low mass, you need the binaries. Supernova kicks, we talked a little bit about those. Eccentric X-ray binaries are interesting in their own. Rejuvenation, when you accrete material in binaries, it makes the star look younger. That's something, certainly something it's been observed in many massive star binaries particularly. We didn't talk about disks around these systems. I've been doing a lot of work lately on circumbinary disks. I'll give you a talk on that sometime. But it's all in the code that we've put out and it is publicly available. Please do go have a look. Look on the Slack channel, there's stuff there. So what is in this code that you can do? Well, it's got a stellar evolution component, which is the binary C code. That's a binary stellar code. And it's fast. Okay, that runs in a tenth of a second for the full evolution usually. We've got a Python front end to that. Okay, so this binary C Python, which I will encourage you to use. And from that, you can compute your populations, all of your rates, number counts, chemical yields if you want. And from that, you can also do galactic chemical evolution. So you can do all of this. You don't have to, of course, it's much easier just to do a few demos, which we're going to do today. There's a lot of case studies. I'll just put a list of these here for people that are interested. If you're interested in how we go through these things, you'll get all these slides so you can have a read through. We do a lot of stuff on chemistry of stars. We do a lot of stuff on rotation with stars, mass functions, 1A supernovae, all these things. If you're interested, these are here for you to just go and have a look. If there's one thing that piques your interest, do go have a look. Some new stuff we've been doing lately. I did some work on carbon over nitrogen abundances as a function of mass to look for merger products in the thick disk. It turns out we see them. They're there. It's natural. Who would have known? We've done a lot of stuff lately on nova rates as well to try to predict type 1a supernova rates through noving systems. I showed you this earlier, so I won't go through this again. This is our circumbinary disks. We've also been putting in a lot of work on tides and also improving the stellar evolution library that's in the code. But technical details. If you're interested, catch up on Slack and I will talk about it there. If you can't be bothered to go through all the examples that I've made for you in this and I've put on the Slack channel, you could just go to the online interface and just type in a few things and hit go. So at the online interface, you can enter the masses for the star, you can enter the different stellar types, the metallicity, all kinds of things. You can put them all in the boxes, very, very easy to do, and then just hit evolve, and you end up with some results look something like this. You get your pretty plots on the right here showing you when stars are evolving through their Roche lobes and things like this. So if you're interested in that, this is a very simple way to do it. It's not as powerful as doing it yourself using the binary C Python, of course, but it works and it's kind of fun. And people do use it. I know people use it because when it breaks, someone changes the server a bit, I get complaints. So I do know people use it. The binary C Python module, I highly recommend you have a look at. This is very, very easy to do. We have everything is, if you're a Python fan, you know exactly how this works. You just load in the module and you hit go. Essentially, you put in a few computational things and you hit go. You can run single stars. You can run grids of stars. It's fantastic. It's really, really cool. So David has done a wonderful job. That's David here. Please say thank you to him if you see him, because he's done a wonderful job developing this and getting us up into the 21st century and making sure this works very, very well. So I've made a few example scripts with this for this school. So the page for this school, I've put the link here. It's in the Slack channel, the Binary Pop Slack channel. You can't miss it. You need to install the code to run it. You can either use the VirtualBox installation, very easy. It's just a virtual machine. You load VirtualBox, you load the virtual machine, hit go, it just works. Very, very simple. Or you can build the code yourself. All the code is free. Okay, it's all available to download for free. If you're using Ubuntu, or if you're using an Ubuntu virtual machine, maybe, there's a simple install script, which I've put in the instructions there. You can just download that, hit go, and it installs everything for you. But it also compiles on OS X and Windows. I've had a student in Canada I've been working with who's been using it on the Linux subsystem in Windows. He said he got it to work, no problems at all. So hopefully it works for you. Now, in OS X, I don't have a Mac to test it on. So we have tested it on Macs, but you may have to install the build tools and stuff like that, and a compiler, of course. But I'm here on and off this week. You can come and ask me on the Slack channels. No problem at all. You can always email me. It's no problem. So there's a load of notebooks. For those of you who know about Jupyter notebooks, that's exactly what we've developed. David's written a load of tutorials, which you can go through and you can have a look and you can see how things work if you want. These are more based on teaching you how it works rather than the physics. But it's still very important. If you want to try actually doing stuff yourself, these are the good place to start. There's full documentation at this page as well, so everything is laid out beautifully like you'd expect for a Python module. I've made some notebooks myself. Have a look at these ones to start with. This one here is still work in progress. I will update you on that later in the week. But there's a notebook for making Hertzsprung-Russell diagrams. Unlike Mesa, it doesn't take a few hours. It just takes a few seconds. It's fantastic. So you can make your Hertzsprung-Russell diagrams. There's a couple of notebooks on luminosity functions to back up the stuff we did this morning on luminosity functions. I've put one on common envelope evolution, which makes this plot, which looks just like the one that I showed just now. I've also put something about some rocks in orbit around the sun. So this is a simulated solar system. There's a planetary module in there as well, so you can have a look at that. It's very simple. Anyone who wants anything complicated, feel free to put it in, because I need help with that. But you can try all of these. They're all there. They all just work. They all are on the virtual machine. You can just go there. You can just download it and just run them. Very easy. Now, a quick word, because we've got 1 minute left, a quick word on the future of population synthesis. Now, a lot of what I do relies on these fast models. Will we need those forever? Well, I think for at least a little while we will, because computers are not 1,000,000 times faster than they were 10 years ago. It's not going to happen, I think, in the near future. Maybe quantum computing can get us there, but at the moment I don't think it'll happen. So we're still going to need those because the parameter space we want to explore is so huge. But there's been a lot of progress in statistics and how we handle these things, particularly the big data sets, for example, coming out of Gaia, and how we deal with those. And things like machine learning are certainly a way forward to do some of the work in this. But I think the biggest challenge is that we don't have enough smart people working in this. So I highly recommend that if you think you're smart and you can do this, then please do go there. Now, I found this wonderful image of smart people. There we go. Really, that's what it said on the image. So I may have only gimped it a little bit, so it should be okay. But really, we need smart people to work on this. We're already working on improving the code so that instead of using these fitting functions, we use tables of models from Mesa. They're not perfect, but they are a lot better than what we had before, which is great. We get a lot more physics out of, say, Mesa models or grids of any stellar code model than we do just from fitting functions. So that is certainly something that is happening. And also every year people are working on improving the physics that goes into these models. I'm working with people in the Netherlands at the moment who are working on how stable the mass transfer is, for example. Absolutely vital for all kinds of things, not just neutron stars, but also 1A supernovae. So there's still a lot of people working on this. But I think how we extract the data from things like Gaia is also vitally important. How do we use the data in Gaia to say what happens in the binaries? And I think that is still something that people are working on. And I think it's not an easy question to answer. It's actually very hard. Great, so that's me done for these lectures. Thank you very much for listening. I will be online, hopefully, if my Airbnb's Wi-Fi stands up. Hopefully I'll still be online, and you can ask as many questions as you want. So thank you very much.